Hey guys, today in class we talked about arc length, area of a sector, and angular and linear speed. I know that sounds like a lot of things to talk about, but they're all very closely related, so it's not actually that many new concepts. To start with, I always like to think of these problems in terms of real life problems because they're sort of boring. And so for our first example, we're thinking about Pittsburgh and Miami. They lie on approximately the same meridian, which means the line of, let's see, flat longitude. They lie on pretty much the same longitude line or the same meridian. Pittsburgh has a latitude of 45.5 degrees north, and Miami has a latitude of 25.5 degrees north. So if I were to draw a picture of the situation, which, by the way, in these problems I think pictures are always pretty helpful, I'll draw sort of a crappy version of the Earth, my pretend circle. Here's the center of the Earth. And the longitude lines are the ones that go up and down, and the latitude lines are the ones that are flat. Okay. And so if I think of Pittsburgh as being somewhere up north, and Miami as being somewhere closer to the equator, because they're warmer, right? These are on different latitude lines. And the angle between them is going to be the angle between 40.5 and 25.5. So if this guy is at 40.5 and this guy is at 25.5, I can subtract to find this angle in between them. So 40.5 minus 25.5, let's see, I'm going to borrow 10 minus 5 is 5. We get 15 degrees between them. Okay. So now I want to find the distance between the two cities, which means I want to find the distance along the circumference of the Earth, right here. Okay. So what I'm looking for in this situation with distance is I'm looking for what we would call arc length. I want the length of the arc going around that circle. Now, there's a fancy formula in your textbook. We're not going to worry about that right now. We're just going to use common sense. For this, if we can find the circumference of the entire circle, we're just going to take a fraction of that circumference, and that's going to give us our arc length. So to find the circumference of the circle, circumference is 2 pi r. So 2 pi in this case times 3,960 miles is the radius of the Earth. Okay. And now that's going to give me the circumference of the whole circle. I'm not going to worry about multiplying through and dealing with the pi yet. I'm just going to leave it in the problem. So I'm going to do 2 times 3,960, and I get 7,920 pi. And the units here are miles. So this is my total circumference, and now I want to take a fraction of that. Well, 15 degrees is out of 360 because there's 360 in a whole circle. So I have 15 out of the 360 degrees, and I'm going to multiply that fraction, that proportion, by 7,920 pi, and that will give me my approximate answer. So let's see, 15 divided by 360 and then times 7,920 pi gives me about 1,036.73 miles. So it turns out that arc length is just a fraction of the circle. Now in class today we saw that there are other ways you could do it. You could turn this into a percent. So when you did the 15 divided by 360, if you look, you get 0.04 or about 4% of your circle. So you could also do like 4% of this circumference. There's other ways to do it. This is just one way. The big thing is you just have to remember that arc length is a portion of the circumference of the circle. All right, next looking at area of a sector. A sector is just a part of a circle again. We have an irrigation system that's using a straight sprinkler pipe 200 feet long. So you've got some pipe that's 200 feet long, and it's pivoting around a central point. So it's going around in a circle again. And it's doing just fine, except for that there's an obstacle that only allows the pipe to pivot through 240 degrees. So let's see, it can go all the way around 240. It's going to be somewhere past 180, but not quite to 270. So it can only water a portion of the circle. This part right in here is getting watered and the rest isn't. Well, this time instead of talking about circumference, we're going to talk about area. So area of a circle is 2 pi, oops, sorry, I got confused there, pi r squared. Easy to do. They both have pi's and r's and 2's, just in different places. So here's my formula for area. So my area of this circle is going to be pi times 200 feet squared. 200 squared is, let's see, 4 with 4 zeros. So what, 40,000 pi feet squared? Okay. And again here we just want a proportion or a fraction of this entire circle. So 240 degrees is to 360, and then we're going to multiply that by our total area. So let's see, 240 divided by 360 times 40,000 pi gets us about 83,775.8 feet squared. And I know I'm not really going to significant figures here. I probably should be, but I'm not a math teacher. Science teachers, go ahead and be angry with me. Anyway, the main idea that I want you guys to get out of this is, again, we're just doing a fraction of the circle, so we're using that fraction in front of the whole circle, and that's giving us our answer. And this area in here, this part of the circle that we shaded in that we're finding the area of, anytime you're finding just a part of a circle, it's called a sector. And some of you may have heard this from like throwing shot or disc in track and field. You're throwing in the sector. It's because it's part of a circle. All right, the last example we're going to look at today has to do with linear and angular speed. So in the setup this problem, we have the Earth rotating about the Sun once every 365 days. If the radius from the Sun to the Earth is 93 million miles, we're going to find the angular speed the Earth is traveling, and we're going to find the linear speed. Now here, the difference between the two, let me draw a picture, because I love my pictures. So we've got the Sun kind of in the center of my circle, right? And we've got the Earth out here traveling around the Sun. So I'm going to say S for Sun and E for Earth, right? And the distance between them is 93 million miles. That's a long ways. Okay. So if I wanted to find just the speed that the Earth is traveling around the Sun, I want to know speed is distance over time. So I'm actually going to do the linear speed first. So let's see, speed is distance over time. So let's see, I've got to figure out the distance it's traveling. Well, that's going to be the circumference, because distance is always circumference. And circumference is 2 pi r. So 2 pi times the radius, 93 million miles. Right? And this is per unit of time. And we know that it goes through this unit of time. It goes once around the circle in 1 year, or in 365 days. So right now we've got the total distance the Earth is traveling over the total time it takes it to do that. And you could have said 1 year or 365 days. It doesn't really matter. Okay. The only thing is, in the problem it said find the linear speed in feet per second. So here's where some of that unit conversion that you learned in advanced algebra or stoichiometry that you learned in chemistry comes into play. We need to get from miles per day to feet per second. To do that, I want to get rid of miles. So I'm going to put miles on the bottom. And oh man, this is millions of miles. I'm going to actually write this out as 93 million. So I'm going to put my zeros in. That way I don't have to worry about this million there. Okay, so now we've got miles here, and I'm going to put feet on top. Now the miles are on the bottom in stoichiometry because if you have miles on top and miles on bottom, they're going to cancel, so that unit cancels out and leaves us with a unit of feet. And I know that there are 5,280 feet in 1 mile. Now I'm in feet and I need to get to seconds. So to get to seconds, let's see, I'm running out of space here. I'm going to go ahead and bring some of this work down. So I have 2 pi times 93 million times 5,280, and I'm in feet now. And this is over 365 days. Okay. Now let's see, I want to get rid of days, so now I'm going to put days on top because I want it to go away. And the closest unit of measurement for time to days is hours. So I'm going to put that in hours. Well, I know there are 24 hours in 1 day. I don't want to be in hours though, I want to be in seconds. And so now I'm going to go to the next closest unit of measurement of time, to hours is minutes. There are 60 minutes in 1 hour. So then let's see, hours cancel out. And now from minutes, I can go to seconds. So let's see, minutes go on top to cancel out with minutes on the bottom, and seconds go on the bottom, and there are 60 seconds in 1 minute. Okay. So now the units I have left are feet and seconds, which is what the problem asked for. Okay. So I'm going to go ahead and multiply top times top, and then bottom times bottom, and then I'll divide those two answers. So on my calculator, clear that out. Let's see, I've got 2 times pi times 93 million. Let's make it 6 zeros. Good. Times 5,280. And it ends up with a big number. And I'm going to divide that by 365 times 24 times 60 times 60. Notice I put parentheses here around the bottom part of my division. What I need to tell the calculator is to divide by everything that I'm putting on the bottom right now, but I need to tell it what's all together it goes on the bottom. I'm going to close that parenthesis, and I get, let's see, 97,834 we'll just leave that off because it's going to be 0.07, but we're talking about the Earth and how fast the Earth is moving in feet per second, so I don't think that matters very much. So the Earth travels 97,084 feet every second. That is kind of crazy when you think about it. That's really fast. So this is what we would call the linear speed of the Earth. And linear speed is the speed that we're used to. It's the thing that we use kind of in everyday life. Angular speed is the thing that we are much less used to. So the Earth out here, he's traveling at 97,834 feet every second, right? So as he's going around this circle, that's how fast he's going around it. You guys know though from experience that if you were closer in, if you weren't 93 million miles out but were somewhere closer in here, you wouldn't have to go as fast to stay in pace with the Earth as you go around the circle. This is kind of like when you're running in track and field, or if you've ever run around the track like in gym class. Right, here's my like silly track. If you're the person on the inside lane running, you don't have to run as fast as the person who's running on the outside lane. Like if you're ever trying to run side by side with somebody and you have a conversation with them, you guys know that whoever's on this outside has to run a lot faster to keep up with this person. The reason being is they have to run a lot farther in the same amount of time. Well, the same thing is true here. The closer you get into the center, the slower you get to go to keep pace with somebody farther out. Well, so angular speed is what would happen at the center of the circle. So if you were just the person at the dead center of the circle and you were spinning, so basically like if I could put my pen top right here and just spin my pen, right? It's the like rate at which my pen is spinning from the center with no radius whatsoever, or actually with a radius of 1 theoretical unit. So the difference here is linear speed has an actual radius of, like, in this case it's 93 million miles. Angular speed has a radius of 1 unit. Okay. Now, for this problem, since we already know what linear speed is, 97,834 feet per second, and we want to get to radians per minute, we're actually just going to use this and go off of it. So if I'm at, let's see, 97,834 feet per second, I want to get to minutes. So I'm going to put seconds on the top and minutes on the bottom. There are 60 seconds in 1 minute. So that'll multiply by 60. And now I need to get rid of feet. And I need some way to get rid of feet and to get me into radians. So I need a comparison factor. Here at the unit circle, once around the unit circle, it has a radius of 1 unit, is 2 pi. So 2 pi radians is equal to 1 revolution. And once around the whole circle, my circumference, which was this big crazy number, is 1 revolution. So that's 2 pi times 93 million miles. And since these are both equal to 1 revolution, I can use this as my conversion factor, which actually up here, I'm gonna make life terrible by trying to go backwards. I'm actually gonna scrap this. I'm gonna come back down. Sorry guys. Write angular speed down here. These are times when I wish I was better at video editing. So angular speed, you're gonna take 2 pi radians. And we do 1 revolution every 365 days. So notice we're kind of starting out in the same way that we started out with linear speed. 1 revolution in 365 days, because that's our time period. And then we just want days to go to minutes, basically. This is going to be much easier. So here's my 1 revolution, 365 days. I want to get rid of days, so I'm going to go to hours. Oops, days on top, hours on bottom, 24 hours in a day. And then we'll go to, from hours, we'll go to minutes. So hours on top, minutes on bottom. There are 60 minutes in 1 hour. So let's see, days are gone, hours are gone, and now we're in radians per minute. So from here, we can just simplify. Let's see, I have 2 pi rads over whatever 365 times 24 times 60 is. So let's see, that's 525,600. Okay, and then let's see, we're in radians per minute, so I just need to do 2 pi divided by that, whatever that is. So 2 pi divided by second ANS. Ooh, and it is really little. So this actually comes out to something that's so small. I'm actually just going to simplify the 2, and I'm going to leave this in terms of pi because this came out into scientific notation, and that's always just kind of gross and hard to read. So let's see, 5,200 or 525,600. Isn't that in that song from Rent? I would start singing now, but that would be embarrassing. So let's see, that would go in 262,800 times. So we're going to get pi over 262,800 radians per minute. Okay. One last thing. I know these have been long notes. I apologize. Hopefully you've skipped through some of my rambling. There's a relationship between linear and angular speed that we noticed today in class that's kind of a nice one. And it's that linear speed is equal to the angular speed times the radius. So sometimes if you see, like if you have the linear speed and you want to get from linear to angular, you can just use the radius. You could divide by the radius, and that would be your angular speed. It might not give you the right units. That's kind of the way I was trying to go up here using the linear speed, and the units were just going to be kind of gross. I was going to have to convert back, but you could do that. So this is just a nice relationship to remember. But at the end of the day, if you forget it, it's fine. Linear speed is just distance over time. Angular speed is just distance over time too. It's just distance around the unit circle. So maybe go ahead and add that into your notes. Distance around the unit circle. All right, that's it for your very long notes today. Hope you have a good night. There will be practice problems on the blog, so make sure you get those before or you go to bed or maybe when you get up in the morning. All right, thanks guys. Have a good night.